Welcome back to Home Learning. This is computer science and the topic we're going to look at today is sound. First off, Mr. Holton's going to give you an overview of sound and how it works in computer systems. Then that is going to be followed by an activity and an exam question reviewed by Mr. Barnes so that you can check your work.
Let's cover sound then. So you're listening to me now and you're listening to a digital recording of my voice. When I'm speaking to this in a room here, it's actually in an analog form. So when you're naturally speaking to somebody right next to you, the sound will be travelling to you in an analog form. And what a computer needs to do is convert that into a digital form, usually with the use of a microphone. And then it will take the sound and it turns it from analog to digital through a process called sampling. Okay, sampling, that's an important word to remember. And what it does is this: at regular intervals, it measures the height or the amplitude of the sound wave. And I'll show you what I mean by that. So let's pop the graph of a sound wave on the right hand side. So what I'm going to do is draw a kind of a sound graph, the likes of which you've probably seen in sort of like a physics lesson. So let's do like a wavy one like this. And because I'm doing a graph, I should do two things. I'm going to label the axes. So this bottom one here is the sound wave over time. And you're wondering what this, what the y-axis is. Well, that's this thing called amplitude. So that's the height of sort of the sound wave. And I've got two things that I need to consider when I'm capturing this sound and converting it from analog to digital. The first is how often I take a measurement of the height of that wave, and that will be called the sampling rate. So I'm going to write that here. And the other thing is how many options I have to measure the height of that wave, and that will become a bit clearer in a little bit when I talk about the bit rate, so how accurate I can get the height of that sound wave at any given point. And what I'm going to do is just start off with a fairly low sampling rate. So I'm going to draw, say I've got samples say every second or something, and draw 5 things along the bottom there. And let's say I haven't got very many options to choose for the height of my sound wave, so I've got quite a low bit rate as well. And sampling works like this: every time I take a sample, I look for when I can next take a sample according to my sampling rate, and I match the height of the sound wave to the closest bit rate that I've got. So that's going to be here, that's going to be probably here, here, so because it matches up over there. This one matches up to this one here, and then this one, probably about that one there. Okay, so that's the samples that I've taken. But if I draw a line between these dots, if I join the dots up, you'll see I haven't really got a very accurate representation of my sound wave. Every time that line is not matching what's on my sound wave, you're going to hear it. Your ears will pick up that it's not exact. Okay, so that's what we're going to do to start with. We're going to take this sound wave. I'm going to just save it for a little bit later. I'm going to show you how we can get a slightly more accurate sound wave. And the first thing that I can do is increase the sampling rate. So instead of taking samples every second, maybe I change it so I'm taking samples every half second. So let's do the dots for that. I'm still restricted with my bit rate here, so I still have to match up to one of these 4 different options along the left hand side, but let's see how we do. So I'll speed this up a bit so you don't have to hang around. Here we go. And let's join these dots up. And as you can see, I'm still a fair way off my sound wave here, but I've probably got a better representation of the sound than I did do originally. So if you compare these two here, I'm doing a little bit better. So by increasing the sampling rate, I've got a slightly better representation of my sound. The other thing that I can do is increase the bit rate, so I can give myself more options to choose from when I'm recording the amplitude of the sound. So let's do this once more with a higher bit rate and sampling rate and see if we get any closer. Let's join up these dots. Whoops, forgot one. Let's do that one there probably. So again, it's not perfect. It never is going to be. It's never going to be as good as analog sound, but we're much closer to the original sound wave if we compare this one to the original one with a low bit rate and a low sampling rate, to increasing our sampling rate and then eventually increasing our bit rate as well. We get much closer to it. So you might ask, well, why don't we just have the biggest possible sampling rate and bit rate? It's not as simple as that, because every time we increase the bit rate or the sampling rate, it increases the file size as well. So the trade-off for quality, if we ever want higher quality for sound, is that you're always going to end up with a higher file size too. And that's sampling of sound.
So now Mr. Holton's given you an overview of sound and how it works in a computer system. you need to have a go at converting analog sound to a digital string of binary zeros and ones and then plotting that onto a graph. What you will notice is that when you change the sample rate, you will see a difference between the analog, which is the original sound as you're hearing it from somebody's voice or from an instrument or something, and you'll notice a difference between that and the digital version of that sound. You've got 10 minutes to complete this task because there's a few graphs for you to do. Off you go. And that's time up, so we're going to go over to Mr. Barnes, who will review your answers.
Okay, so let's have a little look at this activity that's getting you to complete your own sampling, converting an analog sound wave into digital, much like a computer would. The first one was done for you, just to give you an idea of what we were looking for. So here we've got the sample rate of 1 second. The sample rate is the number of times in a given time frame that the height of the sound wave is analysed. And then we've got a bit depth of 2, and you'll see on the y-axis here we've got 2 bits in binary, which means we can store 4 different frequencies. So with this first one, and it's not an exact science with the way we've done it, if you measured every 1 second, we've got at 0, the height of the sound wave is 0, 1, so I've wrote 0, 1 here. At 1 second, it's somewhere in between 0, 1 and 1, 0. I think it's closer to 0, 1, so I've put 0, 1, but it's understandable if you put 1, 0. For the next sound wave, at 2 seconds, we're probably going up to about 1, 0. So you notice here I put 1, 0. At 3 seconds, we're probably closer to 0, 1 again, so I put 0, 1, and then at 4 seconds I've put 1, 1 because it's up there. And then all I've done is I've gone and plotted that sound. Okay, so at time 0 I've put 0, 1, at time 1, 0, 1, and so on. So now what we're going to do is basically the same task but with a different sample rate. So let's have a little look. So now I've set a sample rate of every half a second. So I'm going to do the same thing again. So at 0 I've got 0, 1, so I'm just going to write 0, 1 in here. And then half a second, I'm probably just going to go 1, 0. At 1 second, 0, 1. At 1.5 seconds, I'm probably going to go 0, 0. 2 seconds, 1, 0. 2.5, 1, 1. At 3, I'm going to go 0, 1. At 3.5, probably going to stay with 0, 1. And then at 4, 1, 1. So I've plotted it again. Notice I've got more samples. So what that actually is going to mean is that I've got a greater file size straight away because I'm storing more data. And then I'm going to plot it. And let's have a look at how close to the original it is when I plot it. So at 0, I've got 0, 1. At half a second, I've got 1, 0. And excuse me not using a ruler. And then 1 second, I've got 0, 1. And then at 1.5 I've got 0, 0. And then at 2 I've got 1, 0. And then at 2.5 I've got 1, 1. At 3 I've got 0, 1. At 3.5 I've got 0, 1, and at 4 I've got 1, 1. So it looks something like that. Now hopefully what you'll see straight away is this sound wave is closer to the original than the first example, and that's because I'm sampling it more often. So if you increase the sample rate, the good thing about that is you're going to improve the accuracy of the sound to the original because you're sampling it more often. However, the drawback is it's going to store more data because you've got more samples to store. So in this example at the top, I've got 10 bits, 10 zeros and ones to store. In this next example, I've got 2, 4, 6, 8, 10, 12, 14, 16. I've got 18 bits of data to store, so almost double the amount of data to store. Let's go on to the last example. So the last example, I'm keeping the sample rate at 0.5 seconds, but I'm increasing the bit depth. Okay, so the bit depth is the number of bits used to store each sample. So I've got a bit depth of 3 bits now, which gives me 1, 2, 3, 4, 5, 6, 7, and it should, if it was needed, give me 1, 1, 1, which is 8. So it gives me 8 different frequencies. Okay, so let's do the same again. So this time 0, 0 would be 0, 1, 0. Half a second's going to be roughly 1, 0, 1. 1 second is 0, 1, 1. 1.5 seconds is 0, 0, 1. 2 seconds is roughly 1, 0, 0. 2.5 is going to be 1, 1, 0. 3 is going to be 0, 1, 1. 3.5 is still going to be 0, 1, 1. And 4 is going to be 1, 1, 0. Okay, so straight away I've got 9 samples here, and I've got 3 bits per sample, so that's 27 bits I'm using, rather than the 18 of this one and the 10 of the first example. So now let's plot it. So at 0 I've got 0, 1, 0. At half a second I've got 1, 0, 1. At 1 second I've got 0, 1, 1. And then 1.5 seconds I've got 1, 0, 0. At 2 seconds I've got 1, 1, 0. At 2.5 seconds 0, 1, 1. And then 0, 1, 1. Oh, have I missed one? 0, 1, 0, 1, 0, 1, 0, 1, 1. Oh, I've missed one. Whoops. So 0, 0, 1, 1, 1, 0. That's going to be very confusing to finish off. And then, right, so now I'm going to join them up. So I've got 0, 1, 0. That goes to there. That one goes to there. After the third one, it's going to go down to here. The fourth one up to there. The fifth one. Excuse my mistake. Okay, so once again it's been plotted, and you'll see maybe very slightly compared to the second task it's got a slightly more accurate representation again, because this time I've got a higher sample rate and I've got a higher bit depth, which means I can store a greater range of sounds, which means I can get it closer to the original. So in short, what you end up with here is if you increase the sample rate and you increase the bit depth, you're going to increase the accuracy of the sound and make it better quality. The trade-off with that is you're going to end up with more data to store, because you've got more bits to store than you would if you had a lower bit depth and a lower sample rate. So it's going to take up more storage space.
So using your new knowledge of digital sound and how it works, you're now going to complete some exam questions. You've got 10 minutes to complete them. Good luck. Off you go. And now we're going to go back over to Mr. Barnes, who'll review your answers.
Okay, so let's have a little look at these few exam questions and model some answers. So we've got, when recording a sound file on a computer, the sound needs to be sampled. Describe how sampling is used when storing sound. So we've got 2 marks. We need to make a point and expand on it. So, sampling. This is when the height of a sound wave is measured at regular intervals and converted into digital. I'm going to put /binary because that's what it ends up in. Okay, so 2 marks available here. Let's have a little look at the mark scheme. Okay, so we've got the height / amplitude of the sound wave is measured. So I've got the height of the sound wave is measured for 1 mark. At regular intervals, 2 marks. So I've already got the 2 marks by this point, but just for completeness, I made sure that I talked about what it ends up as, so it's converted into binary, which is actually also in the mark scheme. So we've got 2 marks there. Perfect. Okay, moving on to the next question. Explain the effect of the sampling interval on the size and quality of the sound file recorded. Now the key thing here is it wants you to say what happens to the quality and the size. Now what you need to be careful of here is not sitting on the fence and just going, yeah, the sound quality goes up. Up if what? Okay, so first thing I'm going to say is if you increase, I've left it in purple, never mind. If you increase the sample rate, then this will increase the size of the file as there will be more data as there are more samples to store. Okay, now I need to talk about the quality. The quality will improve as the sound will be nearer the original as more samples have been taken. Okay, let's have a look at this. Okay, mark scheme. So we've got here, we've got here, if the interval is smaller, or if you sample more often, you have more data stored. So I said if you increase the sample rate, this will increase the size of the file as there will be more data as there are more samples to store. So I've got more samples to store, 1 mark, and I said it'll increase the size of the file. So you'll see that's on the second point here, so the larger file. And then I've said the quality will improve as the sound's nearer to the original as more samples have been taken. So again, but the sound reproduces closer to the original, so better quality. 3 marks. Okay, let's have a look at this last example then. State the effects of increasing the sample rate of the recording. So it's a state, so it's 2 marks, so you get only 2 points here. So what happens if we increase the sample rate? Well, I'm going to say the file size increases, and I don't need to explain why here because it's a state question. The file size increases and the sound quality improves as it is closer to the original. Okay, let's have a little look. Push that up. So we've got here on this last question, just about see it. So we've got the file size increases. So there's 1 mark. And I've said the better quality because it's closer to the original. 2 marks. And there we have it. 3 perfect model answers.
And that is everything you need to know about sound. Stay tuned next time.